Hey, Hugo.
Hey, Joe.
Hi.
Hi, Julie.
There's a question from the Lifecycle Working Group, which we'd like to raise if it's possible during this meeting.
Sure. Hey, Justine.
Hi there. We also have Shitish, our master's student who's working on Linux kernel support for
Hi, everyone.
and so
Yeah, Julie. What we'll do is, all right. So we need to end. How long do you think it'll take, Julia?
Probably no more than like 2 or 3 minutes.
Okay,
But
we'll do that one first. Then once we have quorum,
okay.
and that way, then these guys can have the rest of.
Oh, yeah. I just hopefully this is a quick procedural thing.
Okay.
Thank you.
It usually takes us, 3 or 4 minutes to get people on. So.
when I was in grad school, we talked about Berkeley time where everything just started 10 minutes late by default. And so then people would waltz in 15 minutes late.
In some communities, we have what we call universal greeting time, where we just kind of go, "Good morning," and never acknowledge that there's an end of day until when you say good night when people are leaving for the day.
All right. While we're waiting for the last couple of people to join, what's the topic?
The emergent item is the lifecycle working group is currently without a chair. The chair has been deployed to war. We do not know how long he will be away for. One of his immediate or direct coworkers essentially has indicated that they don't know when he'll return. So what we're hoping to do is name a new chair. The group has consolidated, it seems, around myself to serve as that intermediate chair until Gal is able to return.
Oh, so he got caught up in those.
Yeah, unfortunately.
Yeah, that is quite unfortunate. Oh, I'll fix the formatting later, but how do I want to put this? I'm just going to leave it at that. And all right. So I think what we do is, so I have no objection whatsoever. I think that's quite reasonable to do. So why does anyone else have any discussion or objection? All right. Okay. So Julie, you're it.
Awesome. Thanks.
Yeah, that's unfortunate, and
It
we have to
happens.
do something.
Yeah, no, we've been operating, hoping it was just 2 weeks, but it's clear that's going to be longer. So,
Okay.
Thank you.
Okay.
Hi, Julie. I've heard you speaking in the working group meetings. Which company are you with?
I work for Red Hat.
Oh, for Red Hat. Okay. Yeah, I support it as well. I was just wasn't clear to me which company you're with. Thanks for.
Yeah, I'm taking a very neutral approach. More of my goal is to just build consensus and move us forward. So
That's kind of the OPI way.
Yep. Thank you.
All right. Yeah, that's great. So so we have quorum with the technical steering committee. So I talked to Justine and her students a few weeks ago, and about the INSO project, and we thought it might be interesting for you guys to hear it, see what you thought, as a possible collaboration, information, incorporation of open source into the OPI libraries. Any combination of things is allowed, of course. We just have to decide what makes sense. But at a minimum, education would be really valuable. This is a really interesting project and set of techniques that they've developed. And it's well worth your time to hear them. So with that, I'll turn it over to you, Justine, and I'll stop sharing so you guys can share.
Awesome.
And I guess introduce yourselves a little more formally, and take it away. And we can use. Oh, does anyone else have any other topics? I know we have one topic pending, but I want to let the chat threads play out before we make a final call on that one. And Dan, I'll talk to you a little bit about it as well offline. But I don't want to do a rambling discussion about it here. Okay, Justine, take it away.
Cool. So hi, everybody. Thank you so much for joining us. My name is Justine Sherry. I'm an associate professor at Carnegie Mellon. My research is in pretty much everything to do with network systems. My background is primarily in network functions virtualization. I did some of the early work on characterizing middle box deployments and sort of exploring what it would take to move that kind of functionality to more cloud-like environments. I've been at Carnegie Mellon for 7 years, and in the last couple of years, we've been looking at how server architectures need to change to better support high input-output systems. In particular, I came to that because the network functions that we were building were running into a lot of really interesting bottlenecks that were driven by the server architecture itself. Hugo is one of the star students of this project. He's going to be graduating in probably 2 or 3 years. He won he was the first person to ever to win Best Paper Award and Distinguished Artifact Award at the Operating Systems Design and Implementation Symposium. And so he has this new approach that he's designed for better integrating DPUs and SmartNICs into the server and allowing more efficient exchange of data between your DPU and your CPU. So I'm going to let Hugo introduce himself and then present the talk. The other person we have here is Kshitij Rana. He is a master's student, and for his master's thesis, he is developing ENSO support for the Linux kernel. Right now, ENSO is a fully kernel bypass system, but it doesn't have to be that way. And so Kshitij is developing sort of the Linux hooks for that. So I will let you talk about ENSO.
Yeah, thank you for introduction. Yeah, I'm a PhD student here at CMU, working in Justine. I work mostly on designing new NICs and that includes new interfaces, but also new functionality that runs in the NIC as well. So let me talk about ENSO. Share screen first.
This people window is gonna block the screen share.
Yeah, a minute,
If you just click.
but I can see my mouse. Okay. Is that better?
If you click the little one, it'll totally flatten.
Okay.
Yeah, there you go.
Okay, can everyone see the slides?
Yes.
Thank you. Yeah, so I'm going to talk a little bit about ANSO, which is this new stream interface for NIC application communication that we developed here at CMU. Okay, so you folks are probably very familiar with these two trends we're seeing in high-performance networking. On the NIC side, I've seen this increasing number of offloads that increasingly operate at high network layers. And on the CPU side, I've seen over the last years more and more the use of efficient network stacks. They often use techniques such as kernel bypass and rely on batching to reduce per packet overheads. But where I've seen like a lot of improvement on both the NIC and the CPU over the last decades, the way the NIC and the CPU communicate has been surprisingly unchanged. And they communicate using this packetized interface. So in this talk, I'm going to first show that there is a mismatch between how the NICs are used and the interface that they provide. And then we're going to show that by fixing this mismatch, we can really improve performance while also paving the way for even higher level offloads running on the NIC. Also feel free to interrupt at any point if you have questions. So before I talk about this new interface, let me first quickly describe the existing interface. So the high level point is that the existing interface is a packetized interface. And what I mean by this is that every packet that comes in the NIC, we're going to allocate a dedicated packet buffer in host memory. So now every packet the NIC is going to copy to its own dedicated fixed size packet buffer. And there are three main problems with this interface. The first is the abstraction itself. And that is because if you want to implement high-level offloads on the NIC, such as RPCs, application-level messages, or the transfer protocols, now this interface forces the data to be chunked into these packet buffers. So say you have a message that spans multiple packets, and the NIC successfully reassembles the message. But even though the NIC knows the message boundary, it now needs to split the message among these different fixed size buffers. And before we deliver that to the application, we need to recombine the pieces. And if we implement something like TCP that has a byte stream, there's not even a concept of boundary, and you may need to collect the pieces at any point and deliver that to the application. The second problem is a poor cache interaction due to this phenomenon we call chaotic memory access. So even if you have no offloads on the NIC, because each one of these packets is sent to a separate packet buffer, when software finally needs to access the packets, it needs to jump around to unpredictable memory locations. And as a result, it's hard for the CPU to predict what the next cache access will be. So even if you run the PDK with a simple echo server using the latest Intel NIC, you see as much as 55% miss ratio in the L2 cache, only because you need to jump around to these different packet buffers. The third problem is the overhead with metadata. And that is because this interface uses not only packet buffers, but also the descriptive ring buffer to coordinate the buffers with the NIC. So even before the software can receive any data, it first needs to post these empty packet buffers to the NIC. And it does that by sending these descriptors over PCIe. And now for every packet, the NIC needs to not only write the packet, but also write a new descriptor to inform the software that a packet arrived. So, especially if there's any small requests, you actually become bottlenecked by PCIe before you become bottlenecked by Ethernet. So you can see in the same echo server, using mean-sized packets, you see as much as 39% of your PCIe bandwidth being used only with metadata. And not only that, you also consume a significant number of cycles coordinating these buffers in the software side. And I show you like the process to receive data, but I have a similar process for transmission with similar problems. Okay, so I argue that there's a mismatch between how the NICs are used in their interface, and these 3 problems that I show you, the result of this mismatch. Are there any questions so far? Okay. In that case, the next one question to ask is, can we do better? Can we design a different interface that will better align with the requirements we have today? And our proposal for such a new interface is ANSO. And ANSO is a new interface for NIC application communication. And the key idea is to provide a streaming abstraction. So ANSO provides this new primitive we call an ANSO pipe. And NICs and application, they can communicate among each other by pushing byte streams over this ANSO pipe. So what exactly do I mean by a streaming abstraction? What I mean is that we're going to provide the illusion of an unbounded buffer. So instead of having the packet buffer per packet, now we're having the packetized abstraction. In a streaming abstraction, I have a single unbounded buffer where we can push arbitrary bytes contiguously one after the other. And this is extremely flexible because you can use the same abstraction regardless of the offloads you have on the NIC. So even if your NIC has no offloads, we can still use an ANSO pipe to push raw packets by writing them back to back in the same byte stream. But if your NIC is aware of application level messages, we can now write complete messages in the same ANSO pipe. And if your NIC implements a transfer protocol such as TCP, it naturally fits this abstraction because you now write a contiguous byte stream over the ANSO pipe. So given that we have this very flexible abstraction, now there are 2 main questions we need to answer. First is how we implement this. And the second is how does that actually help us with performance? So let me start with the first one. So recall that we want to provide the illusion of an unbounded buffer. And the way we do this is that each one of these ANSO pipes consists of a single contiguous buffer. And then we're going to treat this single contiguous buffer as a ring buffer for data. So that means we're going to have a NIC pointer and a CPU pointer. And whenever we need to push data from the NIC can write data contiguously in the ANSO pipe, and it can advance the pointer to notify the CPU that more data has arrived. Okay, so how does that help us with performance? If you look at the 2 performance issues I highlighted before with the packetized interface, so poor cache interaction and metadata overhead. In ANSO, because memory access is naturally sequential, it's very easy for the CPU to predict what the next cache access will be. So as a result, ANSO can reduce cache misses by orders of magnitude. And because we can write data back to back, we no longer need to notify every packet, we can notify batches of data at the same time. So that also helps us reduce the same metadata traffic significantly. Okay, so ANSO gives you these performance improvements, but there are actually a lot of challenges you need to address in order to make it efficient. And the first challenge is actually how we're going to have the NIC notify each batch efficiently. Because naively, what you can do is that for every packet that you put in the pipe, you can send a notification from the NIC to the CPU. But if we're doing this for every packet, we're going to reintroduce the per packet overhead that we're trying to avoid in the first place. So we need some sort of technique to try to suppress some of these updates and only tell software that we have more data when it actually needs to know about the data. And then also we combine 2 different techniques. Yes?
Oren has a question for you. If
Oh.
you know. That he raised his hand in the chat box.
If that's okay to stop you for a second.
Oh yeah, of course.
So the first of the problems you mentioned is about assembling the message from the different packets, and you didn't mention it here now.
Right.
And I wonder, I mean, we cannot assume that the same message will come in consecutive packets, right?
Right, right. Yeah, so good question. So answer is like this primitive that allows you to push byte streams from the NIC. So the way you're going to answer depends on the functionality you have on the NIC. So if a NIC doesn't implement any offloads, you will be pushing raw packets over the same pipe. So you still need to recombine them to assemble a message in software, if that's the case. But what is interesting is that if your NIC can also reassemble the messages, now we can push complete messages through the pipe, which was not possible before with the packetized interface. Does that make sense?
So a NIC that can compose the messages is that, I mean, I know the RDMA protocol, right? Like Rocky. So that's what you mean.
Yeah, so it depends on the functionality. If your NIC can do it, then it can push entire messages.
Okay.
But if it cannot, then it will also just push raw packets. And you still need to do it from software.
Okay.
Yeah.
Got it.
Yeah, and if the NIC or DPU were able to reorder, then that gets rid of part of the problem, and so you can have an intermediate solution as well. At least that's what I take away from listening.
Exactly.
So it's a spectrum of possibilities depending on the offloads.
Yeah.
Which is one of the reasons we have such a hard time defining anything, is because there's like 18 ways to do it. You know, you could do. So yeah, this is good. Yeah, it's a good.
Yeah, just to be clear, so from the three problems you mentioned, the first one actually depends on such capability in the hardware, while the other two are, we just show how this can resolve.
Exactly. So the first one is like arises when you have these high level offloads, but it's not really a problem if you know. Yeah. But the other two, they happen even if you don't have offloads. Any other question? Okay.
Yeah, Hugo, I'm interested if I start stacking many messages or objects into my pipe, then how do I find them? How do I find the boundaries?
Good. So usually in a message, so if you have a packet, for example, you can look at that packet header and know the limit. So we're assuming the message you also have some kind of like message header that will tell you the size. And for byte streams, you actually need multiple pipes in order to multiplex them. So yeah. Make sense?
You're assuming that somehow I'm aligned with a message. It has a TLV header type length value. So that then I know, hey, if I go ahead this length, I'll find the front of the next message.
Exactly.
And I can continue to do that.
Yep. Okay. Yeah, so I show you how answer can help you with the two problems that I showed before. But now I'm going to talk a little bit about how we implement answer efficiently. And one of the challenges is actually how we determine how often you should send an update to software. Yeah, so I told you that like sending an update for every packet would be inefficient because they were reintroducing per packet overhead. So in answer, we actually have two techniques that we combine in order to notify batches efficiently. The first is reactive notification, and the second is notification perfection. And the idea for reactive notification is that the NIC already knows how fast the software is consuming data from how fast the software is updating its own pointer. So what we do with reactive notifications is to send updates from the NIC in reaction to the software updates to its own pointer. So let me show you an example. So when the first piece of data arrives, the NIC will send an update by advancing its pointer. But if more data comes after, the NIC will suppress any update until after the CPU consumes the first one. And then it can send a reactive notification pointing to the very last piece of data. So this is nice because if the CPU is consuming data faster, we're going to send more reactive notifications. But if the CPU is low, we can have data accumulate and send fewer notifications. And this is actually enough to ensure they only send notifications that are strictly necessary. But the problem is PCA latency. And that is because suppose you have this scenario where you have a batch with 2 packets. Now the CPU is going to process the batch. But also the CPU pointer and the NIC pointer meet, we need to wait up to PCA RTT until we receive a reactive notification from the NIC. Because it will take a PCA RTT for the NIC to receive the update from the CPU and send a response back. And only then the CPU can process the next batch. So that both inflates your latency and also wastes cycles because software is idle, waiting for a notification, even though there are packets already there. So we use the second technique that we call notification prefetching that allows software to explicitly request when it updates from the NIC. Is that a question?
Sorry, no, it was me coughing.
Okay, no worries. So the way this works is that even before, I think there's something in the chat. I cannot really see the chat. Can someone?
Sure, I'll try to watch it for you. And
Okay.
if it's important, I'll interrupt. How's that?
Okay, thank you. Yeah, so what we do with notification prefetching is that even before we consume the first batch, the software explicitly tells the NIC that it's going to need a new notification soon. So now while it processes the batch, the NIC can send the next notification. So now when we're done, we can move on to the next batch right away.
Yeah, and there's a question about the parallelism, Hugo,
Okay.
from Asim, not able to get off mute and raise hand. And the question is, do we mean that we will have an application stream per flow represented in the NIC? So this is the flow to application stream parallelism question.
Yeah, exactly. So you can have multiple ones of these pipes. And you can have, for example, a pipe per application thread, or even multiple pipes per application thread.
Asim, does that answer? All right, keep going. Asim can type additional stuff if they want.
Right. And there are many other design challenges that we had to address in order to make it efficient. Unfortunately, I won't have time to talk about them. But I encourage you to refer to the paper if you want more details. You can also ask if you're interested in any one of those. Okay.
A quick question.
Yes.
Did you compare your approach to things like busy polling and interrupt coalescence and other approaches that are in the these designs in the kernel already, in
Yeah,
DPDK
so
already?
we compare mostly against the PDK, which is kind of like the state of the art in network, like host networking performance. We don't really compare against Linux because it tends to be lower performance than the PDK. Does that answer your question?
Yeah, and when you are looking at, you mentioned that the packet buffers are kind of strewn across. That's is that a artifact of how the software is written, or is that a necessary condition? So if you're trying to improve the cache performance, you could approach it the other way and start looking at where those buffers are how those buffers are being allocated, and try to improve it that way. When you say it's a big performance jump, are you comparing it to the sort of DPDK default or to a optimized caching HOMO driver? Like what's the baseline?
Yeah, that's a great question. So yeah, it's actually a really good question. So we compare against default DPDK, but the problem is actually fundamental because you don't know ahead of time what the packet size is. So you always need to allocate a packet buffer that is big enough for the maximum packet you may get. So even if you allocate these buffers one after each other, you're still gonna have these unpredictable jumps, depending on the packet size that you get. So there's no allocation strategy with the packetized interface that can address the caching problem. Does that make sense?
Yeah, and then did you also compare it to the vectorized DPDK driver?
No. So what is that?
The vectorized DPDK driver is the highest performance version of the PMD. It uses the vectorization primitives inside the CPU to batch numbers of packets at the same time for small packet performance and also increased packet processing performance. So you can,
Right, as far as I'm
get-
aware, it does
yeah.
use EX instructions, which I'm not sure if that's the vectorize you're referring to. Or is it a different kind?
It's not on by default. You have to turn it on. Yeah.
No, that's the default. Our numbers are for default configuration.
Okay, thank you.
But like, yeah, I'm gonna show like some of these performance problems that are fundamental of the packetized interface. For example, the PCA bottleneck. Even if you like optimize the software, you become bottleneck in the PCA, even if you have cycles left. Yeah, I'm gonna show a little bit more later. Okay, so because ANSO is a new NIC interface, implementation actually comprises both hardware and software. So how do I actually have a new NIC implementation in Verilog that exposes the ANSO interface? And in software, have a library and a kernel module that allows the PDK style interface with applications directly with the NIC. And because we have an end-to-end implementation, we can actually test this using like a real system. So we test this using 2 machines connected back to back. And one machine will run a package generator, and the other will run the design of the test. And the second machine, we can compare both ANSO and the Intel NIC. And one of the first problems we had is actually because all of the existing software package generators, they're based on a packetized interface. They're not fast enough to stress test ANSO. So the very first application we implemented was ANSOGen, which is a software package generator based on the ANSO interface. And because ANSOGen is based on ANSO, it's actually able to deliver 400 gigabit per second line rate using a single CPU core, which was not possible before. So here I'm showing the performance of an Echo server using ANSO or DPDK as we increase the number of cores. So we can see the blue line, which is ANSO, becomes bottlenecked by Ethernet, even with a single core. And DPDK cannot reach 100 gigabit per second with 1 core, and it becomes bottlenecked by PCIe with 2 or more cores. But I really like what Review D of the paper said. According to Review D, ANSO soundly destroys DPDK for many types of micro benchmark applications that are popular in the academic literature. And indeed, we reported 4 different applications to run on ANSO, and we saw up to 6 times throughput improvement, only by changing the interface with no additional offloads. Now I'm going to talk a little bit about the impact of the 2 techniques I talked before. So reactive notifications and notification perfection. So here I'm showing the latency as increased the load. For ANSO without these techniques, which is the blue line, and for ANSO with both reactive notification and notification perfection. So you can see when we send a notification for every packet, we can only reach around 50 gigabit per second. But if you combine these 2 techniques, we can achieve similar latency with much greater load. And if you compare that with the A10 NIC with the PDK, you see that we achieve similar latency with much higher throughput. And what was also surprising to us, at least in the beginning, is that ANSO can also outperform the packetized interface, even if you need additional copies for ANSO. Because one of the problems you may have in ANSO is that you're putting these packets back to back in the same pipe. So what if you want to send this package to different locations, like in a virtual switch? In that case, you need to copy the packet data to a different location. While in the packetized interface, you can just move a descriptor. But what we show is that Ansel can outperform the packetized interface, even when you need to copy every packet with Ansel and zero copy with the PDK. So I'm just going to talk a little bit about the ongoing work we've been doing Ansel. So what Shitish is doing right now is integrating Ansel with Linux. So what he's doing is that basically in Ansel we have this separate.
Julia just raised her hand, has a question. If this is a good
Yeah.
transition point.
Thank you. Were any benchmarks done with any packet payload size above 1518 bytes?
Yeah. So if you look at some of the applications, well, this one, for example, this one of the x-axis, we're looking at packet size. So you can see the larger the packet, the gap it shrinks because you have fewer per packet overhead.
Mm-hmm.
But it still wins for most packet sizes.
So the assumption is, say, if you go up to 9,000 bytes, it's going to be a flat line, basically.
Probably, because both are going to become bottlenecked by Ethernet anyway. But also have a...
Yeah, I don't know actually what it would look like if I had a 400 gig NIC
and
I had the 9,000 byte frame. We don't have that hardware.
Yeah, because they're no
Okay,
longer
thank you.
for larger packets. But when you actually have application data, so for example, the log monitor application we have here, we're actually using MTU size packets. And you still see almost double improvement in throughput. Because now we're using the cycles for the application as well.
Thank you. I was just curious because I know there's talk of the performance on cards starting to surpass the actual ability for the bus to the system processor to just execute.
Yeah.
So I think at some point you'll flatline them both.
Yeah. Yeah, so what Shitish is doing is integrating Ansel with the Linux kernel, where the Linux is aware of notifications, but we still send the pipes directly to the process. So we can still do zero copy, but the Linux is still responsible for waking the application the right time. So hopefully we can avoid this kind of busy polling strategy that we have with the PDK without a lot of overhead. And another student is working on the latency sensitive process scheduler, where again, we have the scheduler in control of the notifications, and it can also promptly wake applications that receive data. So to conclude, I talked to you about Ansel, which is this new streaming interface for NIC application communication. I showed that Ansel can improve application throughput by up to 6 times, even with no offloads on the NIC, only by changing the interface. But because Ansel also allows easier and more efficient high-level offloads, we're very excited to see what people are going to use Ansel for. So we made everything open source, both the hardware and the software. And we also have full description about how to use the API and the API itself, all documented in this website, if you want to take a look. So I'm happy to take more questions.
Another question from Santananda.
Mm-hmm.
Hi. So these days, Linux kernel, they're adding receive zero copy for packets, right? Where applications do not have to incur copies. But Enso seems to say that you always need copy because the buffer is fixed between NIC and the CPU.
Yeah, so
do you have any plans to reduce that when I have multiplex flows on the same buffer, right? I would have to do copies, right?
Yeah, so the real thinking is that you're gonna dedicate a buffer per application, so you don't need the copies. And our implementation actually supports up to 16,000 pipes, which seems like a hopefully good enough for a reasonable number of processes. And the advantage we can do over what we have today with zero copy in Linux is that today the packetized interface, you basically have a notification for every packet. But in Anso, because you can notify these batches, we don't need to involve the kernel as often as we need now. So hoping that this also will give you better performance because of that.
Yeah, notification for every packet or a bunch of packets is more of a latency question, right? How soon your application needs to know whether you
Yeah,
can
not only latency, but it
batch
also
or
has
not
cycles
batch.
like going through all of them.
It's also a bandwidth question because each one of those notifications takes up memory. You have a descriptor with every notification. And that has to be copied over PCIe.
Yeah. Yeah, so for some of the benchmarks, you actually become bottlenecked by PCIe, even though we have CPU cycles left.
So
that
yeah,
also-
I understand removing the metadata. Yeah. I
yeah,
get
yeah.
it. Okay, thank you.
Yeah. So Shichichi actually has the transmission part ready. And you can easily do 100 gigabit per second with one core, even going through Linux and min-size packets.
So we've
Will you
talked,
be sending this to the forum?
Sorry?
This presentation, will you be sending it to the forum?
Oh yeah, I can make it available. It's actually already available. Now we have the PDF, but I can also send you as well.
Yeah, post a link to the PDF. I think I put it in the announcement. It's your paper, right?
Yeah,
Or-
there's the paper, but there's also the talk. They're both available.
Okay, put the link to that in the chat, and I'll paste it into the meeting notes.
Okay, let me.
so we've been talking both with like people on the software side and the hardware side about, and so we've had some folks who are very excited on the software side, folks who build things like load balancers and a lot of packet processing stuff, because those tend to be the use cases that are sort of throttling on IO. And they keep coming back to us saying that they need hardware support. And so Enso right now is a bunch of Verilog for a Stratix 10MX FPGA. And so one of the things that we're really trying to understand right now is the landscape for getting this interface supported in enough hardware that it is useful for these software people who want to try it out without telling them they have to go and buy an FPGA and replace their NICs.
Right, and that's why it's interesting for OPI potentially, right? Because a DPU and in particular embedded core or a P4 pipeline would be perfect for the NIC side of this software.
Exactly.
And we're always looking for more effective ways to move packets back and forth from the hosted systems. So, or the hosting systems, depending on your point of view. So that's why I thought this would be a good one to put in front of you guys to think about.
One thing that hasn't been clear to us from some of the NIC vendors have suggested that they could support Enso with a firmware update. In which case, like, I am very happy to send interns to go implement that firmware. Other NIC vendors seem to think that it might require hardware changes, which is a much longer process. And so I don't know if any of you, I know that you're sort of a combination of software and hardware people. If you folks have any sense of how much heavy lifting is involved in getting Enso from a purely soft logic implementation to something that is more widely available.
Yeah, I can speak for Marvel. It would be a firmware update for us. Yeah,
That's
it's
actually
not a
very nice to
hardware
know.
change.
That's really, really
Mm.
nice to know. Yeah. And for the firmware, all of that is internal. There's no open source firmware for your platforms, or
No, it is open source.
it is
Oh,
open
it is open
source.
source. Nice,
So
nice.
our firmware is also Linux based. So, yeah.
Oh,
This is the best thing I've heard all week.
yeah, yeah.
That's a master's thesis in a box right there.
Mhm.
I'm gonna do a little bit of Googling about the firmware and the source code. Could I email you or somebody in your group?
Yeah, you can email me, or I can redirect you to the right people. Sure. Yeah, we have heard of ENSO in the OSDI 23, and we have been looking at it as well from that side.
Ah, nice.
Because we saw readily that it could be done on our hardware.
That is really nice.
So, Justine, I think one more thing that would be interesting is for you to talk about, the structure of, ENSO. You have code in open source. You have, in GitHub, you have some students working on it, but what's kind of your thoughts and vision for, ENSO from a project or structural point of view?
Right. So from a project or structural point of view, we are very much at a sort of turning point on basically whether or not we can get traction for hardware support.
Mhm.
And up until about 5 minutes ago, I was convinced that in order to get NIC support for ENSO, I was going to have to send 1 million master students out to go and do internships and like beg and bribe my way
Yeah.
into getting people in there. And if there's open source firmware that we can modify, then I can sort of, build up a team here of students that will build up that open source, those open source firmware implementations. My hope would be that, if other folks are using it, that we could see how the ENSO project sort of progresses. My past open source work was primarily with like the BESS software switch, which I think got like modest traction, but because it's like so closely tied to Nepheli networks, it never really made the shift to being a project that was managed by something like Apache or the Linux Foundation. That the big dream would be that, ENSO would be something that could sort of escape the lab and become an open source, ecosystem of its own. But right now it's a team of, Hugo is leading it. There are a couple of faculty members involved. There are a handful of master's students who are extending it in different directions. And we're just trying to push it as far as it can go right now.
Any questions from anyone?
So Hugo, what's the model for putting an ENSO interface under an application, besides having to go through DPDK? Or if I want to use SRIOV and I want to be native into the application with ENSO, how do I adopt
so
it?
good question. So the API we provide is actually different than the PDKs because they're providing this streaming abstraction. My claim is actually easier to use, but it's different.
And you would have to port the code. So I think we should find somebody to build a DPDK library on top of ENSO, which would give up some performance. But I would bet that we still get some more GoFest out of it, even though we have sort of repacketized the API on top of it. But that would certainly give us this sort of drop-in portability that we don't have right now. Right now, we have an API that is better aligned with the streaming abstraction, which will get you more GoFast, but will require a little bit more elbow grease to move from your existing APIs.
So if the northbound API looked like a socket, wouldn't that fit well with what you're trying to do?
Yeah, so our API resembles a little bit more like a socket, but we want it to be zero copy. That's why it's not exactly the same.
Well, there's a trade-off between performance and ease of adoption, right?
if you're okay with copying, then we can make exactly like a socket API.
Because there's also a need for not just streaming between the NIC and an app, but between app to app, right?
Right.
And we often see stuff get packetized just to go app to app, which is silly.
Yeah, I agree. I actually have like a inner process queue implementation that looks more like
Right.
Ansible. That is
Yeah,
also
or things have to pass back through Linux, right? Which
Yeah.
is also kind of nasty.
Oh yeah, it actually performs quite well as well because for the same performance reasons.
Yeah,
That's a really good point.
and small modifications to a socket interface have historically been able to handle zero copy, right? People at different times in real-time systems would do effectively zero copy sockets with a few tricks. So it more or less behaved like a socket, but again, you did have to treat it a little different, right? Because you didn't read and write in quite the same way to the socket. So yeah, it's interesting discussion, Tim.
There was a discussion about the vectorized DPDK comparison. I think I found the info that we need, but I was wondering who was it who brought that up so I could double check with you that we found the right thing so that we could get the right benchmark.
Yeah, that was Dan Daly. He doesn't.
Dan Daly. Okay.
Not paying attention.
Okay. I will.
Actually, I think we lost him.
I'll email him to ask about it.
Oh, it's gonna show a demo. I forgot. Let me show you that it actually runs.
Yeah. do a little 5-minute demo and then we'll close the call.
Yeah, I'm just gonna run an echo server. So we have like two machines. They're connected back to back. They both run Ansible. So this one on the left has a echo server. It's using a single core. I can also show that.
You should check. Is this readable?
I don't know. Yeah. Can you see what's happening?
Yeah, it's good enough.
Yeah, so you can see we're running a single core. And now on the right, we have the Ansible Gem packager. I'm gonna send a PCAP at like full 100 gigabit per second. And that's a 64-byte packets. So now on the left, you can see we're getting 100 gigabit per second with 148.8 billion packets per second, only echoing the packets back. So yeah.
I have this running joke that every graduate student in network systems has to write a packet generator as part of their PhD, which I did this. Everyone has done this. But I think that Hugo is the most justified in having to have had done so because there was no packet generator that could keep up with the load that he was able to process.
There are some open source that you could use. We're trying to create some model-driven open free stuff. So maybe I can talk to you offline.
Yeah, so like the DPDK package gen, which is like one of the fastest ones that I'm aware, was not fast enough. Do you know any other one that is faster?
And I guess maybe the free one might be using DPDK. So maybe it's all the same. So I'm just commenting about every student writing their own versus using common and keep building.
It's using the Wind River packet gen days of yore.
Yeah, so just I'm gonna show this as well. Like I have if you're interested about the API, you can look at the parameters on how you receive data and such. So for receiving is actually pretty nice because you can receive a batch of packets and you have like an iterator that you can go through. So it's very easy to use. For transmission is a little bit different because you have this like buffer that it's like has the unbounded buffer abstraction and you can keep like extending the buffer as you need it. But it's all like described if you're interested in knowing more.
Yeah, great. Hey, all right, any final question? All right, no, this was great. So we'll there's 2 or 3 follow-up questions that we'll do offline. And thank you very much for coming in and talking to us. It was excellent as always, from you guys.
Thank you very much for having us. That was great.
Thank you so much. I'm going to follow up to get a better baseline for the vectorized DPDK. We're going to dig into Marvell's firmware and see if we can maybe get support there.
For sure.
And then we continue to have on our to-do list to assign somebody to doing a DPDK and a socket like API.
Yeah.
So we will keep you posted with updates there.
Yeah, great. And you know, I think the question on jumbo frames is relevant to
Also, yeah.
a lot of the real world transports you see in the industry. You know, in particular,
Yeah, we'll see what we can do about that, because I think it would be most interesting to test that at higher line rates, and we don't have those cards, but we could probably get some.
Yeah.
That's right. Well,
400 gig PlayStation 5.
Well, no, so even when we had 10 gig Ethernet and even 1 gig Ethernet, jumbo frames were a thing. Jumbo frames have always been a thing for storage networking in particular. We always turn on jumbo frames.
Yeah, so I'm very confident in saying that 100 gig, you're going to see a flat line between ENSO and DPDK with jumbo frames. The question I have is, if you're going up higher than that, I don't know what we'll see.
Well, yeah, so you will see 400 and 800 gig coming. Those switches are out now.
This is the first meeting I've heard 800. Here we go.
Yeah. So there are switch chips that do 800 gig per interface, and there are NICs coming that can do 800 gig. I mean, there are 400 gig NICs in production right now, and there are 800 gig NICs coming fairly soon. And those are important for subsets of the industry that will leverage DPUs and offloads heavily, in particular, AI training workloads needs those kinds of bandwidths for parameter exchange. And in fact, to optimize all of that, there's an industry consortium called UEC, the Ultra Ethernet Consortium, which is set to optimize everything under the sun related to capping tail latency and improving RDMA style performance over networks and everything in between. And it's also hosted under the Linux Foundation now. It just formed out of a private consortium that was doing work for the last 15 months to 24 months, depending on how you count. So those speeds are coming. They're real. GPUs are, can generate massive parameter sets that you have to move as quickly as possible across, tens to thousands of GPUs.
Yeah.
So yeah, 400. I mean, again, you can get 400 gig NICs today. So.
All right, we'll go shopping.
Or and there'll be a variety of them by the end of next year. And then, like I say, 800 gig is coming. Absolutely. All right. So we'll close the call. Thanks, everyone, and talk to you next week.
Thank you.
Thank you. See you.
All right. Thank you all.